Sure, we have power now? Yeah?
Yeah,
All right, good.
like you're coming through.
So the title of this talk is the 5 stages of scale, measured off of the 5 stages of grief because the process is very similar. So let's jump in just to why you listening to me. Perhaps not. I've been in the biz for about 2 decades, working on network applications for the internet. And I spent about half of that time in the world of online advertising, which you might boo and hiss, and I would understand. But the secret about online advertising is that's where there's huge amounts of scale. So I've been working at places like Google, Yahoo, Overture before then, Rubicon project as well. And, you know, I got to see a pretty extreme one end of the scaling spectrum there, but I've also done a number of startups, including the place where I am right now, chill.com, which is a relatively small startup that's just coming out there in a big way. And I've seen both ends of the scale problem, and through a whole lot of what could be best described as hard knocks, I've learned a thing or two along the way. And out of kindness for anybody else who hasn't been through these steps and through this painful process, I thought I would share what I've learned along the way. In terms of this type of stuff I work on, I'm actually not, strictly speaking, an ops guy. My background is more on software development side, but I'm one of those people who can't keep their hands out of everything and sort of embrace the whole DevOps principle, always wanting to know and operate the underlying pieces of the platform that my stuff ran on. And I spend a lot of time recently working on big data analysis and big web server scaling type work. So I just have to start talking about the elephant in the room because we've got 2 talks in a row about scale. Everybody's all excited about coming to scale, and geez, the conference is called Scale. Scale is not a real word, not the way we use it. Okay, this is what the dictionary says scale is. By the way, scalability is the ability to scale in the dictionary. So this has nothing to do with anything you guys want me to talk about, I assure you. You don't want to hear anything about stripping off scale. So yeah, it's a made-up word. As a consequence, I can define it how I like. So I'm going to do that for you. And really, I'm going to try to do it in terms of what everyone's talking about when they say scale, which is when they're making up a word, what they're really talking about. So this is what happens when you first build an app. You can draw these little graphs showing, let's say the bottom part is the number of users who are using the system. And you see we have one graph on the left that's looking at the throughput of the system, and another graph that is looking at the response of the system, how long it takes for the system to respond to those users when you have that many people using it. And you can look at that and you go, hey, you know, we just got this up and running. We got a few people using the system. And my goodness, I can see exactly how this is going to play out. We can draw some lines, put some error bars on them, and we can see this is how throughput's going to grow as we add more users. And look, responsiveness, it just stays flat no matter what. We can just keep adding users. And so someone, and I'm sure it would be no one in the room now, but someone who's probably very competent at something else will then go from here to here. Okay, they'll say, oh, I can extrapolate. I know where this is going to go once we have 1 million users. It's going to be just fine. Anybody who's been in this business for a while will tell you that is absolutely ridiculous. The ride is not that simple, and frankly would call someone who did this an idiot. Scalability, though, it's about saving that guy's job. So he's made the bold claim, oh, no, it'll just grow and we'll be fine. And your job, should you choose to accept it, is to keep him from getting fired for saying that. That's what scale is really about. So there's an old joke about when back in the days of the Soviet Union, when a new ruler came on board, he found a nice little note from his predecessor that said, you know, I'm sure you hate my guts, but, you know, out of respect for the institution and our country, I, welcome you into your new role, and I'm going to leave you. I've left you with 3 envelopes. And they're to help you in times of crisis. When you hit your first moment of crisis, open the first envelope. When you hit your second moment of crisis, the second envelope's for you, and the third one is for your third moment of crisis. And each of these will help you address the crisis. When the first crisis comes, he opens the first envelope, has 2 words in it. It says, blame me. He says, that's a pretty good idea. So he blames his predecessor for everything that is wrong in the world. Works well, he gets through, and then things get much, much worse, because that's how they go, especially back in the old days of the Soviet Union. So there's a much larger disaster, but he's thinking to himself, oh good, I still have 2 envelopes left. I'm going to open the second one, and this will save my bacon. So he opens that one. It says, reorganize. It's great. So he fires all of his underlings and hires a whole new staff, and he blames them, the people he fired, for all of his problems. And he says, ha, we're going to make it through. And then he gets to the third envelope, when his third horrible crisis is, and he's thinking to himself, I have no idea how I'm going to get out of this one, but thank God there's that envelope. He opens the envelope. The envelope says, open up 3 envelopes. So I'm going to give you 6 envelopes because I'm a nicer guy. And we are going to go through the envelopes that you need to get through scaling, at least as it's played out for me. Now, technically, actually, I'm actually giving you 7 envelopes, but I'm hoping nobody in this room needs this envelope. This is the first level of scaling problem that anyone ever runs into. It used to be a big deal. These days, it's such a common thing that no one even thinks about it. It's when you run out of CPU power. Your application's running and it's using up more than what one CPU can handle. The answer is more CPUs, more boxes, a load balancer to split loads between them. And guess what? It's really easy to partition CPU load. You can scale that way forever. And this is where that stupid graph starts to become the bane of your existence because, oh no, we can't scale. And then the DevOps guy shows up, he hooks up a load balancer, suddenly, oh, we're scaling beautifully. Oh, great. The next time we have a problem, it'll solve itself the same way, and we'll just keep riding on this merry little ride, and we will scale forever. Yeah. So anyway, I'm going to just assume that everybody knows how to handle this problem and skip past it onto the more interesting envelope. This is one that probably, if you've been having to deal with scaling systems in any significant way, you have been to this destination too. This is the world of read caching. Basically, you've got a lot of people that are hitting your service, but there's this wonderful thing called Zipf's law, which says that the distribution of unique activities on your site will follow an inverse curve, which means most of the requests that are coming in are going to be the same as all the other requests coming in. So if you cache, you can save yourself a lot of operational overhead. And it's nice because unlike the previous one where when you're scaling things, you're increasing capacity in a nice linear fashion. That seems pretty awesome. But linear is really just barely making up for that guy's expectations, right? This one you can actually beat it because the probability that they're going to hit the cache is so high that as the traffic increases, it only grows log in terms of new unique requests that are getting past the cache. So there's a lot of trusted products and solutions for this. This is not a hard problem anymore. There was a day when it was, but it's long since passed. This is where people pull out reverse proxies, they pull out memcache, or if you really want to do it right, you go to the experts and you use a CDN. And you say, here, take care of my problem for me. And it's great. It feels like you can scale forever. And again, people get this false sense of security that, oh, this was an easy problem to solve. I just paid someone some money and the problem went away. This works out until you've got about 200 writes per second. And I'll explain why the 200 writes per second shortly. But around 200 writes per second, you got a problem. And the reason is, we're talking about read caching here. It's not helping you with the writes. Every write that comes in is still got to do something. And so you have great scalability on the read side, but the write side, you're in trouble. Fortunately, most people doing network applications, the reads tend to be bigger than the writes, so this actually buys you a lot of time. But sooner or later, you're going to have trouble. So what's behind door number 2? So yeah, I summarize this as get a real persistence framework. Okay, don't mess around. I actually will argue that people frequently skip over this step, partly because they're dealing with really bad persistence frameworks, and the lesson they've learned is, oh my God, please get me out of this mess. I don't want to deal with this stuff. So actually using a good database that knows how to do concurrent reads and writes, very helpful. A database that knows how to use data structures to optimize its reads and writes and lookups, that will also get you a tremendous amount of room. Back in the day, before Moore's Law had been able to multiply a few more 100 times, it seems like, this would limit, you could only handle a small number of users, even if you had all of this right. But these days, Moore's been very good to us. This will actually get a lot of people very far. You might not need to get past this stage, which is why I want to emphasize that doing this part right can really make a big difference for you. So, the essence of this is having your database be smart so that it can handle lots and lots of concurrent writes and still behave reasonably. It amortizes the behavior over, taking 10 writes and making them look like one to the underlying hardware. You can have a queuing system so that anything that doesn't have to be done right immediately can be put onto a queue, and then they can be processed in a batch to minimize how many unique writes are going on. You can do event-driven I/O so that you don't have a process blocked while it's waiting for some sort of disk write to complete or network activity write. Transaction monitors, similar kind of business. Those are not very popular these days. And then you can go one step further, and actually basically any real database unfortunately really does this, which is cheat on ACID. Okay, everybody thinks of ACID as being this this really important fundamental principle about databases. It's really important, and it certainly makes your life a lot better when you can do it, but if you just cheat a little bit on it, you can get a heck of a lot more performance. And in fact, almost every database product that's out there cheats a little bit on ACID in some way in its default configuration. You can tweak it back to have it really be honoring ACID properly, but most of them have a built-in cheat. And usually the cheat that they play around with is the consistency or the durability cheats, where they're, for example, being optimistic about how consistency is going to play out, and then when they're wrong, things get a little bit more difficult to untangle. Since usually you don't let that happen in your application, the performance win is pretty huge. The big one, though, that you can really make a ton of extra throughput on is D, durability. So there was a great presentation I saw 4 or 5 years ago that was when NoSQL was really kicking up a lot of storm, and the various RDBMS guys were really feeling like they'd been kicked in the teeth 1,000 times, and they couldn't, no one was giving them any respect. And I believe it was one of the Postgres guys said, if we just turn off this fsync operation that we do after every transaction, let's look at what the performance looks like on Postgres when we do this. And sure enough, it suddenly had numbers that rivaled most of the NoSQL solutions that were out there. And of course, most of the NoSQL solutions it was competing with weren't doing fsync. That was how they were getting faster, right? So turning off fsync entirely is kind of a little scary. You have to do a lot of things to mitigate the problems that might come one day. So I'm not necessarily suggesting you do that, but there's a lot of room to play between turning off fsync and religiously fsyncing every single time that a transaction happens. And you can play around with these kinds of things in most databases with tremendously good results, and it'll buy you a lot with very little effort. So this can get you up to somewhere between that window of 1,000 to 10,000 writes per second. Tends to have to do a lot with the kind of hardware and systems you've got underneath. So there's a little bit of play in there. At some point, this is still not going to be good enough. Okay, and this is the chasm that everybody tends to start to have problems with right about here. Although we've been getting better at dealing with it. So let's talk about why this is the particularly dangerous point in this scaling lifecycle. This is a catamaran. If you're not familiar with them, my dad was really big into sailing when I was growing up, and he talked to me about catamarans and regular boats, and we tried them out. And the interesting thing about a catamaran is you actually rarely see them doing much more than this in terms of how much they're tilting. And it's a really great property. They're really fast. They execute beautifully. They can outrun most other boats, and they seem very stable in the water because they don't tilt over as much as a typical single-hull boat. There's a problem, though. They have this tendency to pitch. So what happens is everything's looking fine, everything's looking fine, everything's looking fine, and then with barely a moment's warning, one end dips just a little bit too low, and all of a sudden you're going from, whereas on a regular boat you sort of get to the point where you're almost looking straight down at the water, and you're thinking, I'm going to tip over now. In the catamaran, it's more like it starts to lift just a little bit, and then boom, you're flipped over. Okay, no warning. And this tippiness is a horrible experience for a sailor who's not familiar with it, because you think you're doing fine, you think everything's great. All your instincts from working on a monohull are telling you, we're going to be fine. And then a few seconds later, with just a little bit of a gust of wind and just a little bit extra energy in the system, suddenly you're soaking wet. And if you're lucky, you didn't break your boat. We don't want to do this with scaling, but this happens all the time with scaling. Okay, this is the thing that people have nightmares about. This is why people talk about it all the time in operations and in software development. This is the problem, and it's actually a silly problem because if you think about it for a moment, and admittedly in my case I needed the benefit of hindsight to appreciate it, you can actually see where you're going in this and know how you're getting in trouble. These are some of the technologies that I would describe as being catamarans in the scaling world. Some of it depends on context. Certainly, using a cache for caching write I/O, so like a caching RAID controller or a SAN system that has RAM in it. RAIDs can be a problem in this regard. Threads, it depends actually on the nature of the thread, but certainly if you've got a traditional native OS thread that takes up a lot of memory every time you create one, you can get into big trouble if you have too many of them, and everything looks fine just the moment before. Packet loss, if you're doing your networking really wrong, can actually present this way. Simple reason is that you start losing packets. How do most networking systems solve the problem of losing packets? They send more packets. Do you see a problem here? It happens. However, if you have your system set up, it'll be much smarter about it, and you shouldn't have it. But I've certainly seen it go wrong. And SSDs are arguably in this category, although frankly they only really half get there, and I'll talk about that a little bit later. So if you think about it a little bit, there's sort of some common themes around these things. One of them is that it's all about consuming memory. And the horrible thing about memory is it's really, really fast. And when you don't have it and you have to go to other things, everything else is really, really slow compared to memory. So if you don't know who Jeff Dean is or what Jeff Dean's numbers are, write this down right now. Search on Google as soon as you're out of this talk. Memorize what you see on that page. Okay. This is more important than anything I am going to talk about in terms of understanding scale, but I'm putting it up here to give you some context on this. And this is hinting at what the real underlying problem is, okay, that's driving all this. But you'll notice at the top of the diagram there's some numbers that look really nice and small, like 0.5 nanosecond, 5 nanoseconds, 7 nanoseconds. That's really awesome. And if we go down there, and actually his list goes further than this, is just as much I could fit on the slide. You're at 10 million nanoseconds. You may notice there's some difference between those numbers, right? And they're kind of differences that can get you into a lot of trouble in the real world out there. And you might notice that, hey, most of the stuff above that 10,000 is RAM. And that 10,000 is when I'm not using RAM. And that's kind of the crux of the problem. And what really sucks about this is, again, thinking of that D in ACID, when is a transaction, when is a write really considered done in our world, generally speaking? It's not when it gets into the level 1 cache. It's not when it gets into the level 2 cache. It's not even when it's in RAM. It's got to be on a disk if you're lucky. It might be a disk in another data center before it's considered done, okay? So now you're talking about, wait, that's really unfair. On the reads, you can get by with that 3 milliseconds, right? Or 3 nanoseconds. 3 nanoseconds, oh yeah, sure. The read's completed. 5 nanoseconds, you did a branch mispredict, you got the data, you hand it to the user, we're done. Excellent work. When the write happens, no, that's not good enough. Okay, so one write could exact more toll than 1 million reads. That's the crux of the problem. So if you look, this is a snapshot in time, and actually some of these numbers have already changed, but as I'll talk about, most of the important ones haven't. Here's the real problem. So at the top, throughput has been just going like gangbusters. We're all good friends with Moore, and it's great. We all, basically, all of us become twice as capable in our jobs every 18 months because some guys working in a dark room in a semiconductor design lab have come up with a better manufacturing process and a better chip, and suddenly everything that we do runs twice as fast. It's great. There's very few jobs we can get where this works out. Problem is, that's only throughput. Latency is a somewhat different story, and it's a kind of distorted story, and this is where the really big problem comes from. Because CPU latency, it had almost been following exactly the same growth. Okay, it was going about 2x every 18 months. It kind of hit a wall a few years ago. You may have noticed clock speeds haven't gone up, pipeline stages haven't shrunk. CPUs are basically taking as long to do a single serial operation as they did last year. Okay, there's some tweaks where there's some new instructions and SIMD and stuff like that that are saving our bacon, but for the most part, we're no longer getting the 2x on that. But that's okay. We got a good long ride out of that. We got it forever, it seemed like. Then there's the LAN. The LAN's actually only been slightly behind on that. It's going fits and starts. So we're living in a world of Ethernet. Then suddenly we get 10 gig Ethernet, and then we get 100 megabit and gig Ethernet, and now people are getting excited about 10 and 100 gigabit Ethernet. But you can sort of know that, for a while we're going to get a little bit of pressure, and then magically, the floodgates will open. And actually, that's only at the cable level. At the switch level, it's going in a much smoother path. The switches are getting more powerful and more capable all the time. Memory, that's where it starts to get a little dicey. Memory hasn't been getting faster as consistently over time. And this is the part that you start to see some really funny things playing out in the industry, because tricks that used to seem insane and literally a bad idea are now a performance win because latency to memory has increased. And things that seemed like a really good idea before are now a really dumb idea because latency to memory has not increased as much as, or it has increased more than the speed of the CPU. So a classic example, there's a whole batch of high-performance compression algorithms that get, by most people's standards, really crappy compression. But it can still be, for data that's got a lot of redundancy in it, can be like close to 2x. But the key thing is it doesn't tax the processor very much. And so it's possible for modern processors to decompress the data faster than they can pull it from RAM if it was in uncompressed form. Okay, so you get like a free performance win, and I assure you, 2 decades ago that wouldn't have worked. Okay, but that's not too bad. It's 2x every 3 to 5 years. That's close, right? I mean, that's like growing half as fast as the CPU. Yet disk's not the same story, right? Disk throughputs have actually been going pretty well. We've run into some limits with the individual magnetic disks, but we just group a bunch of them together and we can still get really good throughput. However, latency has not gotten a lot better with traditional hard drives. Okay, it's basically not much better now than it was a decade ago. Maybe if you're really lucky, you could say it's half as much latency as you had before. But even that's really kind of playing around with your budget on your hardware. Not spending a lot on hard drives back then and spending a lot on hard drives now. And so they really haven't improved latency at all. And this creates some really, really interesting issues because what used to work really, really well going to disk and a problem that literally didn't even exist before now completely sucks because your CPU is screaming along 100 times faster than it was before, and your hard drive is moving at the same speed it was before. And then there's the really fun one at the bottom there, the WAN network. So if you actually have to go to another data center, Einstein still wins, right? C hasn't changed. We haven't found a way to modify that, and so we're basically victims to the spoils there. Every now and then they find a fraction of a millisecond they can scrape off because of some inordinate processing overhead that's in a router somewhere. But the the bottom line is usually you can look at a globe and you can calculate your latency to your WAN that way. So this actually creates a really big problem in the data storage space because traditional indexes are actually playing this game the wrong way. They are trading the expense of scanning through data, which is throughput limited, with the expense of randomly seeking for data, right? So the idea of an index is, oh, no, you don't have to scan through all the records in this table. I can tell you that this record, one of them has the right answer. So just go to those, grab it, and get me back the data. And when this technology first came out, when B-trees and hash tables and all that kind of stuff came out, it was awesome. You could go from, seriously, something that would take an hour to something that completes in seconds, okay? But it doesn't work out so well when the latency game starts working against it and throughput starts becoming so much more powerful. And the way I describe it at the bottom is a pretty good way to look at it. If you imagine a world where you've got an index that allows you to quickly realize, without having to look at the records, that only 1% of the records need to be looked at to find the data you're looking for. It says, no, all these other records, 99.9% of them, I know they don't have the record you're looking for, okay? That's great. I can just seek to where those records are, and I'll look through them, and I'll find the data I'm looking for, and I can complete. Or if I have to write, I'll write the data there, and everybody will be happy. So if you've got a world where you have a 10 millisecond seek, and you can scan through 100 records a second, that means that's like, even with only 0.1%, you're getting a 10x win there. It's like free. But then you shift to a world where, let's say seek times have improved by an order of magnitude, which they haven't. But let's say you can go now down to 1 millisecond seek time. But your, throughput has gone like crazy, right? Moore's been our friend. So now we can scan through 1 billion records a second. Great. Now that index is making your operations 1,000 times slower. Because you could scan through 1 billion records to find the one record that you need in the time it would take you to do all those seeks to to consider all the ones that the index thinks might have it. So this is the crux of the latency problem with I/O. And again, because we insist that stuff actually gets to disk, this becomes a real pain in the posterior. So it brings us to envelope number 3, to save your bacon from this mess. That's what I call real partitioning of I/O. And by that, what I mean is breaking down this wonderful model of the RDBMS that's existed for the end of time. Every RDBMS maker out in the world tries to make their database as parallel as possible, but the illusion that they're trying to get to manifest for you is that everything happens sequentially. There is always a serial representation of the moment of truth. Now, they do cheat on that a little bit, but fundamentally that's what it's about. The trend of late to get around from that, a lot of what NoSQL's been about and everything like that is, yes, screw that. We're not going to try to put all the data together in one place and have one bottleneck where there's this one, you can think of it as a metaphysical robot who's sitting there going, yes, this one, now this one, now this one. It just doesn't scale, right? You can only do that so fast and you start to get in trouble. So the solution is, screw it. Don't put the data together. Keep the data apart. We'll break up the data into little chunks, and whenever I need to find the data, I'll know which chunk to go look for. And if I ever need to look at all the data, rather than pulling all the data into one place, I will send out my code to all those little bits of data, have the code do operations on the local little bits, summarize the results, pull those back in. That'll be way more efficient. This is, in essence, what Google's MapReduce paper was all about. It's what distributed hash tables like React and Cassandra and HBase, it's fundamentally at some level what they are all about. You don't bring all this data into one place. You don't try to define specifically what the order of operations was and have one image that represents the moment of truth. You split it across machines, and each of those machines gets to operate independently, and suddenly no more scaling problem. And this is what the cap theory, if you've heard all about that, that's what that's all about. And it's a wonderful solution, and it really has a different principle from these guys, okay? All of these guys actually make your life incredibly easy as long as their capacity isn't maxed out. okay? Because if you have a caching rate controller, I mean, you got to love it a little bit, right? It does make your life really simple. You just put that thing in, and suddenly it's like you have tremendously more power than you used to have. It's just the moment when it runs out of capacity, when it can no longer, it still can only write out IOs at a certain speed, right? When it can no longer fit and absorb everything that hasn't been processed in RAM, well then everything goes from moving at RAM speed to disk speed, which we already talked about is really brutal. This, with this model, it doesn't behave like this because everything is operating independently. There is no, capacity that's in one single place that's being stressed, or at least let's pretend that for the moment. So that lets you go very far, and it can be a very interesting model. And you don't need to use these tools. It's actually most people's applications. You could think of ways to break them up without having to use a sophisticated tool. For example, if you've got customers with accounts that never talk to each other, never see each other, they're just independent accounts that you have that you're providing services to. Well, there's really no reason why you couldn't put some of the accounts on one server and some of the accounts on another server and some of them somewhere else. It's no problem. You can do operations there. If you ever do need to get a summary from all the servers or from all the accounts, well, you can run a report from each of those servers and then aggregate the results. And you haven't used any new technology that you're not familiar with, it'll get the job done. Obviously, if you use some of these commoditized tools, there's some extra benefits that you get from it and a great deal more sophistication. But on the other hand, you can at least limp along in this space pretty safely. So now we come to envelope number 4. So that was really working well for you, and you're breaking everything up, and things are moving along. Until someone says, I need to combine this data here and that data here, and by the way, I need an answer instantly. I can't wait and I can't let you pretend that you can roll this up into 10,000 records, 10,000 different reports, and you just run them in one pass going through the data. I want the answer now. And the solution that has become very popular for this, and I think it's a pretty darn good solution, is to recognize that, okay, you're storing data in these little silos, okay, but the new data that's coming in, it's much smaller than the data that you already have. So rather than trying to, pull all the data that this thing needs in order to do all your calculations on it, instead of pulling all that from these different data sources, doing key value lookups everywhere, why don't you route the data to the different data stores that have the bits of information that it needs. And once it's hopped through all the different spots, you can accumulate and get the result you want. And this can go very quick. So you can imagine, for example, you've got you think of it from a search engine's perspective. You've got a certain keyword that comes in, right? And you want to find, okay, I don't know where all the machines are that would actually have the information about that keyword, but I have a service that stores that information as it accumulates and indexes things. So we'll go there first, and it'll tell me which machines I can go to get the information tied to this search. Then you go to each of those machines, and they're saying, oh, okay, so I have a bunch of keywords, but I don't know which ones are most relevant to this keyword. I just have all these documents, and I know which document is which. So, okay, they pull out all the stuff that they know that's relevant, and then you route the request again to another set of machines that resolve the issue of which keywords are most relevant to this search that was put in. And you can go through all these steps, and as you go through each step, a little bit more information is picked up, but you're not having to push a lot of data over the network in order to do this. This approach is used a lot by systems like Storm, Streambase, ZeroMQ, and it's it's surprisingly simple to work with. I actually find it much easier to work with than traditional database systems, especially NoSQL systems. The one catch is you have to think about your problem very differently, because you have to find a way to organize your islands of data such that it serves the needs of these individual real-time requests that are coming through. But the performance is awesome, because latency-wise, you're only hit, really, potentially, by the one round trip within the same data center. That might be the worst that you get, which is 0.5 milliseconds, right? Because you don't necessarily have to go to disk. Each of those individual islands could have the hot data that it needs in RAM, okay? And you just hop around on the network each time, paying that 0.5 millisecond penalty. That sure looks a hell of a lot better than doing one disk seek, let alone potentially several, right? So This approach works very well, scales very, very nicely until it's not enough. And if you're really lucky, you'll probably never have to open the fifth envelope, but just in case, let's take a look at what's inside. So this one is about cheating on reliability. The important thing to realize is, first of all, you can't always do this, okay? But it tends to make a lot more sense once you get to really big numbers, okay? Once you're dealing with lots and lots of scale. So if you think of this, could get you to easily, millions of requests even potentially that you're processing, no problem, okay, with this model. But, now you're at, billions or whatever per second, data's flying around. How bad would it really be if 0.001% of the time you lost something? Would anyone notice? I mean, I can't count a billion requests out, right? Now, obviously, if there's money involved, somebody will do the counting. It's going to happen. So if you're doing like real world, like if you're Visa and you're pushing money from one bank account to another, this approach may not appeal very much. Actually, I would argue you could do it, but it's just the lawyers and everybody who has the money that's being moved around are going to have you for breakfast, okay? Okay, that's not going to work so well. But there's a lot of other cases, okay, where actually you probably already have more failures in your processing than you would have from, potentially losing a packet here or there, okay? And the other thing is, a lot of cases, you're actually working off of aggregate data on this individual bits of data. So if you think about Google, for example, they're showing, search results for a search keyword. If one of those results missed 1 out of every million times you did the query, how many people are going to be upset about that, right? No one will even probably know. Yeah, sure, of course you would. Yeah, you're so picky. Do you have any experience in QA? Yeah. No, but this is part of the trick, right? The other thing is, ultimately, if no one's measuring it, it really doesn't matter if you don't do it, right? And I mean that not from the sense of no one's going to catch you. It's like literally if no one's measuring it, then no one can tell whether something got lost or not, okay? And so you can cheat a little bit. So you can, for example, there's the old joke, everybody in the networking world, there's always some point in your early career where you try to make UDP go faster than TCP. It never works, or at least if it does work, it's because you cheated somehow. But everybody does it, and they think, oh, look what I've done. In reality, TCP is very well tuned, and it does its job fantastically well. There is one exception, though. If you don't care about reliability, UDP beats the crap out of TCP. It beats the crap out of it. Think of it from this perspective. Remember the speed of light thing, right? For TCP to even get going on its job, it has to do a full round trip because it's checking to make sure it's acknowledged. Now, there's sliding windows and all kinds of other tricks to try to amortize that cost, but in the end, until that round trip is completed, you don't know if you're done yet, okay? UDP, I just fired it away. I'm done. I don't even know. No one has to come back. I'm done. I've gotten twice as fast as TCP without even trying, okay? It's awesome. This is a great way to move along. If you think about most of the reporting that systems do when you're working at this kind of scale, it's questions like, what percentage of the time is the user finding what they want? What is the highest probability best answer for us to give this person? Or even what percentage of our users are logging in and actually doing a login session on our site? These kinds of questions don't need a right down to the individual unit precise answer. And God, do we pay a lot in terms of scalability and performance in order to get that precision, okay? We pay a lot of money for that. It's very expensive. So if you just pull off that shackle just a little bit, and I'm not saying you go, oh, we're going to throw out a third of the data or something like that. I'm saying, no, you'll process all the data, but every now and then, if something odd happens along the way, you're just going to look the other way and keep going, okay? And it's really recognition of the reality that nobody ever wants 100% reliability. What they really want is, I know something might go wrong. When something goes wrong, here's how I want you to solve it, okay? In TCP's case, it's keep trying to get that data until you get the right answer, okay? And by the way, if you really, really can't, just give up and declare an error and tell me that something's gone wrong, okay? UDP's approach and other mechanisms like this is, dude, I just care that you give me an answer quickly, and if you can't get it for me in the next second, I really don't want to know, okay? And that represents actually a large percentage of what people do in systems, whether we acknowledge it or not. The tricky thing about this is that, we're used to thinking of our computer systems as highly deterministic. And so we don't want to get out of that little box of, something might go wrong, and I don't know what's going to happen, and it's going to happen or not. But if you think about it, we're all used to dealing with humans. My God, if humans could have the failure rate of UDP, well, we'd need half as many of you guys, right? I mean, it'd be awesome. But yeah, no, it would be nice. So we already deal with all these high failure rates in every other part of our system. If we just put a little bit of slack in, my God, you can get a lot more scalability almost for nothing. So those are the 5 envelopes, the first 5 envelopes, and we'll get to the last one in good time. I'm sure you can imagine what that's going to look like. But I also wanted to talk a little bit about, constructing these different pieces and arranging them all together and getting them all to work together. That actually has been a lot of what big scaling systems has been about the last 5 or 10 years, okay? And the good news is people are starting to realize, hey, everybody's got the same problems. Maybe we should, combine this into a comprehensive system instead of everybody, finding a queuing system here and a batch processing system here and a real-time processing system here and pull them all together and sort of ad hoc construct something. Maybe we can do a combined system that sort of maybe isn't even necessarily the best in any one of these categories, but collectively works together really nicely and doesn't have any problems with logistics and setup. And that's kind of where things seem to be going right now. You're seeing that systems are combining the capabilities of a real-time key value lookup. So, I just want an individual key like with Memcache or Redis or something like that, with more traditional disk-based storage models that are more adapted for batch processing. Things like, Hadoop. If you think about HBase, sitting on top of Hadoop is a great example of this, right? The underlying HDFS is totally there and ready for you when you want to do your big batch processing on huge amounts of data. But if you need a quick lookup for a single record, by God, HBase has got it in RAM for you, and it'll get it for you quick, okay? Same with writes. You can do writes the same way. So using technologies like LSM-based indexes, so in Cassandra terms, that would be SS tables, but it's basically, just blocks of data that are sorted and nothing else, more sophisticated than that. Clever things like compressed bitmap indexes and various other techniques like that. They're all designed for when you want to look at the data in aggregate, okay? They're useless for you, or close to useless for you when you want to look at individual records. But you can marry them up very nicely with the key value lookup technology and have a little bit of synergy between those parts of the tech stack. And that allows you to move quickly. And then the other big trend that's tied into these sort of combined systems is eventual consistency, because if you don't do that, you're going to be stuck. You're going to have that bottleneck where you're ensuring consistency as you move along. And then the other big element is mobile code. So like MapReduce, like a lot of other things, where instead of pulling all the data in, you're pushing your code out to the different bits of data out there, having it execute and pull the results back. And there's a bunch of systems that are like this, that are sort of combining all these different things. Cassandra was probably the first one that was really going specifically after this target. HBase is doing it. React is doing it in different levels. In fact, most of the systems out there that are under the NoSQL label are kind of moving in this direction in one form or another. And I think, for folks like us who are just, I don't need to make it more complicated, and if people have already solved this problem because people have already had to deal with this scale, it's nice if you've got a combined system that solves the problem comprehensively. I can tell you, when you have things as individual components, you spend a lot of your time just trying to move data from one component to another and make sure that that process is working, which is a whole new problem that you don't have to worry about when it's all managed for you in one system. So I'm going to give you an example of taking advantage of all these things that I've talked about in a very simple way that literally is building it from scratch. It's not even using any of these packages out there. Just, hey, I want to do logging, and we want to do a lot of logging. We've got a lot of systems, hundreds of them, and they're all generating tremendous amounts of data, and I want to track all that. And it would be cool if I could process it all. It would also be convenient if I could know that I'm not going to lose too much data, and that I can, look at my logs anytime I want. So, all right, how do we do this? So I actually built a system like this, and it was very simple. I wouldn't say that it was easy, but it was simple. But first you start with a machine parsable format. Screw the human parsable stuff. That slows down the computer, makes everything less efficient, and also introduces bugs. Computers are really good at parsing things in machine-readable format. And until someone in this room agrees to read a terabyte worth of log data, I'm not going to worry about human format for it, okay? Then each event source, so each machine that's generating this log data, doesn't write to its disk at all. It just writes to the network, okay? So it's going to have this data that's nice and packed and convenient for computers. It's going to push it out to the network. This has a nice property that the latency to write to a network card is relatively constant, not 100% constant, but pretty constant. And it's much more constant if you use UDP multicast to write to it. Okay, why that? Well, because it's really the UDP part. You're not stopping to see if it actually got out the door. You're just firing it and moving on. So this is great. So you can not have to worry about some kind of problem in the log processing system causing your production system to stop, right? And or at least slow down. And multicast is a nice little touch that I like to add because it made it so that any part of the system could grab the log data, so you could have very loose coupling between the different systems. And then because all of this could actually fail all the time, right? You could lose data. We're going to have some redundant listeners that are listening to this data, the same data. Literally, I'm listening to all the stuff that comes from this box, and you're also listening to the stuff that comes from the box, because this way the odds of both of us losing it are much smaller. And because we're using multicast, we don't really pay a performance penalty for each additional listener, because it's the way the network equipment looks at it is it's one packet. It's just one packet that got sent many different places. Okay, so it's much cheaper than send it to him, then send it to him, then send it to him, where it actually gets slower as you add nodes. So here's a sample of a protocol buffer style logging event to give you an idea of what the actual implementation would look something like. It's got a bunch of values identifying which process, which thread, and which session within that thread is generating the event, so you can quickly identify distinct sources of your data. It's also got a sequence number, so that combined with those previous three fields, you can now uniquely identify every single packet that gets generated, but you don't have a common sequence point that you're or a common synchronization point that you're using to say, oh, this event is separate from this one, so I'll give them different IDs. They're all independently being generated. And of course, for free on this, because we're using UDP, we're also getting the IP address of the source. So we can distinguish machines that just happen to have two processes with the same thread number or the same session number. We can still identify them different because we know which machine they're coming from and even which port they're coming from. So now we can identify every single event, and for fun, we put a timestamp in there because time matters. And then we have some logging level tagging on it so that we know, we can filter out events to just the warnings or the errors or the horrible panic moments. And then we have the last field, which is just whatever extra data is involved in the log. So that's a basic logging event. And then you add a separate dedicated channel just for announcing about all the other channels. Okay, so if I'm emitting on a channel, periodically I'll send out an announcement on this other channel saying, this is the world that, this is what I'm doing. I'm sending data here. And you tell them, this is the channel to listen to hear this data. Here's the port to listen on. By the way, this is the last packet I sent out. And, giving you the rest of the stats to give you an idea so you can monitor how the emission's going on. So this is actually very cheap because you might worry that this channel might get kind of noisy as you add more and more nodes. You've got thousands of nodes all sending out announcements. The trick is every announcer listens to the event stream, and it does that to count how many announcements are going out on the stream. And as more announcements come out, it scales back how often it sends out an announcement. Because the reality is, most systems, if I just told you 5 minutes ago that I am sending stuff out on this channel, I don't need to tell you again for a long time because you're going to remember it. And in fact, you can have a directory service that does nothing but listen to the announce channel and just keeps a little table of all the activity going on in all the different channels. It's actually very lightweight. Way I set it up, I think we were going at the total noise on the announcement channel was 100 kilobytes a second, or maybe kilobits actually. But you can tune it however you want. And that was with hundreds of machines. That was still getting a new announcement out about each machine every 3 or 4 minutes. So it wasn't hard to do. Now, that's nice. You got all these events stringing around, but you do kind of want to have some kind of source of truth for this stuff. And so there's a really easy way to do this. We do the stream processing. We have independent machines that are all redundant that are listening to all these events and serializing them in real time, saying, this is what I saw, okay, and putting them in order, and then writing them out to their local disk, which, yes, this is RAID, but this is RAID so that you don't lose the data more than anything else. This is not RAID to get your seeks up. So they are all storing their local copy, and then they're streaming their data back to another stream processor that is just saying, checking to see if they all agree, right? This guy says, I saw this event. So the guy says, I saw this event. The guy says, I saw this event. Well, then that event must have happened, right? But if only one of them saw it, it's like, well, wait, why didn't the other two see it? We've got a bit of a problem here. And this gives you the one thing that you really do want, which I think is important with the data loss thing, is if you're going to cheat here and you're going to let stuff get lost, it's very important to measure how much is getting lost. Because like I said, if you're losing 1 in a billion, nobody cares. If you're losing 1 out of every 2, you're going to have a lot of people angry at you. And the funny part is normally we don't measure how much we're losing, even though we know we're losing some for God knows what reason. Bits flipping in RAM somewhere, a spindle going wrong. We know that every now and then we're going to lose a little bit of data. We never measure it. But you can measure it this way, and then suddenly now you're less worried and have less anxiety about whether you're losing data. So that's what that last little bit is for. And then if you really, really care about getting to the truth, you can even have, the collective log of everything that looks funny where you didn't get all 3 copies of the event that you saw. You can have something like a MapReduce job periodically process all those missing events and say, well, based on the fact that I saw this data here and that data there, I think what really happened is this event got lost. Or I think these 2 machines reordered the bytes for some reason on this event, and this other guy got it right. And I've got a solution there. The key thing is it's working on a very small amount of the data, so you don't even really need MapReduce. You probably do it on one machine, but if you got enough data, you're going to want that MapReduce as just a backfill so you can really get the answer however you want. Now, aside from leveraging MapReduce there, all the rest of the stuff, it's really not that hard to think about how you would build it. You have, on the submitting side, you have a socket. You go, right, that's it, right, that's logged, awesome. For the guys who are combining the data, they go read. They pull off a packet. They might keep a window of like the 100 most recent packets they've seen, and they sort them to make sure that they're in the proper order by source. And then they write those out periodically to disk. Very simple code, right? Nothing complex. You could get really crazy with the batch processing in terms of how cleverly you try to recover the data, but let's face it, we're not going to lose that much data. You don't really need to spend a lot of effort to get really clever there. You might just want to have something for like if for whatever reason one of the journalers goes down and doesn't write out its data to the central source for an hour, that you can recover the data when it finally does show up, right? That might be about as far as you'd want to do. You don't really have to spend a lot of time on it. So what does this get you? This system, personally, I've seen this stuff scaled up to at least hundreds of nodes, and really it can work with thousands without difficulty. Pushing data upwards of 50 megabytes a second over the channel, and that's on gigabit Ethernet networking, nothing fancy there. And pushing data 50 packets per second, that's an aggregate. That's no individual machine is firing 50,000 packets per second. God help them if they did. But certainly in aggregate, that's how much data is firing off. Using 3 or 4 journalers, which the only thing fancy about them was that they had pretty good disk systems that were designed to be more reliable than average. So that was a little bit of cost there. And in aggregate, reconciling upwards of 5 terabytes of data a day. Okay, and packet loss, and actually, I don't remember what the exact number is. I can assure you it was much less than 0.1%. Okay. Now there are a couple of tricks to doing this right. You do have to have your network configured properly. You do need to make sure that you've got a good amount of capacity in the system. Okay, so if you actually have all of your NICs already maxed out, throwing more log data on them is not going to work. But the reality is that it's actually pretty easy to just add another NIC or to bump up the bandwidth on the system in another way. And in terms of the stress on the switches, this actually tends to be less stress on the switches as compared to the normal log shipping rsync process that everybody in this room is doing but not admitting. Why? Because it's when you do an rsync, right, you're aggregating a huge amount of logs, usually stuff that's accumulated over at least hours. You're packing them all up, and you're firing them as fast as you possibly can over the network to the destination, right? So in other words, you're literally telling the switch, run like hell. Get this done as fast as you can. And meanwhile, there's 20 other services running over the network that are doing the same thing. This is very stressful. If instead you do it on this model, it's just as stuff comes in, you sort of trickle out a new event each time, giving a steady flow. It shifts around a bit. It does have one nasty tendency, which is, as you get a lot of traffic, that's exactly the point you're going to be pushing out a lot of logs as well. But all in all, it's actually much gentler to the switch, particularly also because the switch knows it's only going to have to push each packet once, no matter how many places it needs to go, and no matter how many failures there are along the way. So it doesn't have to remember what it's seen, it doesn't have to keep track of all this stuff. The only thing that the switch does have to stress itself out a little bit is the multicast subscriptions. It has to know who's subscribing to what. And that does take a little, I've got to be honest, it does take a little bit of configuration wisdom and a little bit of processing power in the switch, but most switches these days that would be used in a system that's trying to scale to any kind of significant level could do this without any difficulty. So yeah, that brings me to envelope number 6. That's what I got for you.
All right, thank you, Chris Smith. We're going to do some Q&A, and then we'll have a break until the half-hour mark. And Brandon Burton and Chris Tura from Mozilla will talk about their simple scaling. Does anybody have any questions for Chris? Well, I'll just start here and kind of work my way back.
One of the things you mentioned was the anomaly when one box gets an event and say 2 out of 3 don't get it. Is that this, I don't know where you came up with this event, I'm going to throw it on the floor, or uptick that there was a problem in the transmission and look into it?
So that's a good question. And the reason why it's a good question is because it depends. No, the reality is that's actually a really good question the business should have been asking when it was worried about reliability, because really reliability is about trading off performance because there's some level of importance of getting this right? So the question is, okay, well, what's happened here is basically what happens in the TCP case. The packet got dropped twice. Once it didn't. What does the business decide about that? Does it mean that, okay, we're going to take the one that did make it and say that's what happened, and then we just know that there's a certain level of loss that's happening in the system, but we're able to manage it? Or do you say, God, if I've only got one, I'm not sure if I trust that enough. So I'm going to mark this as like, a bad packet, and I'll keep it because I want to be able to investigate this and figure out what the hell happened. But, I want to see at least 2 before I believe it's true. And that's a real business decision that probably should have been made a long time ago, because you're probably already spending thousands, if not tens or hundreds of thousands on trying to make sure that you don't have to worry about that problem. And if you go to the business guy and he goes, actually, I don't really care. And you say, well, would you like to save $100,000 right now?
Actually, this is more of a comment than a question, but I've worked at Yahoo search advertising, and the stuff you said about logging particularly, that was, overall...
That is the first place I saw that implemented.
It was really great, and there are additional benefits to broadcasting your logging, because you can use that as a framework for your automation now. Since it's already built in, there's very little cost, and across the lifetime of the system, the cost of automation testing really goes down when you have something like that. Because I have coworkers who ended up working at AT&T, also in search advertising, and they tell me the pain of automating their test cases versus when they were at Yahoo. Like I said, over the lifetime of the system, it's phenomenal savings.
There's also nothing cooler than like when I want to look at the logs for something, just pressing a button and my little program subscribes to the channel, and without any request to the ops team or any discussion about how this is going to be configured, packets just magically start flowing my way, right? That's just awesome. But even better is, like you talked about, like having this loose coupling between your applications that allows you to make testing easier, to make scaling up the complexity of the system easier. It's great. It's a good way to go, if you can do it.
Is there any way that you could adapt your UDP logging solution to someone like Amazon where there is no broadcast or multicast?
I knew you were going to ask that. Yeah. So yeah, the cloud sucks, right? So here's the truth, right? They could make this work. It's just not enough people ask for it, and they're delivering a commodity, right? And so they don't provide it. You can adapt this, right? There is a price you pay, okay? So switches have dedicated hardware just around, oh, this packet came in, let me send it to everybody who needs it, okay? But there's this thing called a CPU that can pretty much do whatever you tell it, just not as fast or as efficiently as a switch. So you can have and this is actually, you see this in Flume and a bunch of other log aggregation services, you can have a dedicated machine who receives the logs, and then he gets all the subscriptions and he pushes it out. And this is traditionally what queuing stuff is, except most queues are designed around like must not lose. So instead I would recommend something like 0MQ or similar technologies that are, no, let's push the data fast, and if something goes wrong, it goes wrong. But, let's get it out to everybody who needs it quickly. And actually 0MQ is a good model for this because it can be just a configuration change to go from the UDP multicast model to bingo bango, now I'm doing TCP because I'm stuck in the cloud, okay? So that's a good way to address it.
Man, you had a badass presentation. I'd love to talk to you about a million things, but the one quick question is, okay, if I want to make sure I understand what you're saying right, is when you're talking about the heuristics of the disk seek time versus the throughput, and it kind of sounds like a parallel to the discussion that's kind of going on in recent years about how the order of magnitude and latency difference between the CPU cache and RAM, and that no longer use like the hash algorithm stuff because they actually penalize. Is that basically what you're saying? Is that you totally forget about all the disk algorithms and just do straight linear searches in a lot of cases? Is that what you're saying?
So the colloquial joke that was going around for a while was disk is the new tape, right? And that's because relative to processor speeds, right, disk had latencies as bad as tape used to have back when processors were a lot slower. And all I'm saying is, yeah, disk is the new tape, RAM is the new disk, cache is the new RAM, L1 cache is the new register. I mean, it just keeps getting worse.
Hi. Can you give an example or two of some of these cheap compression, decompression algorithms of which you speak?
Yeah, sure. So the one that was sort of the popular known as LZO, and actually LZO really is a collection of compression algorithms that's out there, and he keeps updating it because of the moving target of Moore's law and our other memory bandwidth limitations. What is a good compression algorithm for solving this problem today is different from one tomorrow, because tomorrow there's more processing power and not a lot more bandwidth, so you can spend a little bit more processing power trying to squeeze out a little bit better compression, and you get a better result. So LZO is a library that's out there. It's freely available for open source projects, but for commercial projects there's some licensing entanglements that you will get yourself into, which is why our friends at Google were kind enough, I think, to release a library called Snappy. And Snappy has very competitive performance with LZO, and actually I find in a lot of situations it works out better. There's a few others that are out there, but those would be the two that I would start with, and if you really care about it, you won't have problems finding the others once you got those two.
Somebody from Google had a question.
Yeah, shoot.
It was a mild observation. I was more going to say the is a new tape thing is true, but it's hard to complain about it when you say that.
It's because things have gotten faster, not because they've gotten slower.
The memory is bigger than the disk was back then, so it's kind of hard to complain. But yeah, it's a terrible problem. And
exactly, right? Like, what can you do, right? Actually, I was going to mention SSDs there briefly, and I forgot to go back to it. SSDs have kind of been seen as the savior that's like sort of bridging the gap. It's like, oh, SSDs can be the new hard disk. And that's true, but actually they can be very misleading in terms of how they perform too, because SSDs actually can support a tremendous amount of parallelism. It's absolutely insane, because fundamentally what an SSD is a whole, you can think of it as a whole bunch of tiny little disks, except they're not spinning disks, they're solid state, that are all arranged in a huge RAID of like hundreds and hundreds of units. And so they actually have obscene read speeds. Their write speeds, though, aren't so great. And you can still get tons and tons of writes done at once with them, as long as they're not writes that have to be done one after the other. So like, it's not, if you have a case where you write something to disk, and then your next operation is read back what I wrote to disk, and then add 2 to it, and then write that back. Okay, now that's not going to scale very well in your SSD. In fact, your SSD's write speed, depending on how expensive your hard drives are and how cheap your SSD is, might actually have worse latency for an individual write than the hard drive. Typically, they're a little bit faster, but even then, they're like 3-4 times faster, maybe, at best. And so it's great. I can do 50,000 I/O ops per second on this thing, but if I do them sequentially, I can maybe do 500. Yep.
A lot of us are working on data sets that aren't quite as big as what you were mentioning up there.
Yeah, you don't get to envelope number 6.
Right.
Be thankful for that. Be very thankful for that.
But can I, what would you say is the cheating system of doing a distributed RAID in memory in RAM disks?
You want a cheap and dirty way to do distributed storage in memory?
I'm doing a bunch of RAM disks and making them look like one RAM disk, one RAID.
So if you don't care about it looking like a file system, I would say just use Redis or something like that, right? If you just want it to be records that are key value that you look up and you have a certain amount of flexibility. If you really need it to look like a disk, right? There's actually...
Well, sure, because that's what my scripts are all written as.
Yeah. No.
Files.
If you want it to be a disk and you got file systems and stuff like that on top of it, you can actually make a RAM disk on Linux and export a network block device on it, and then RAID those over
a bunch of $100, $200 cheap machines.
Yeah. No, and you'll get fantastic performance. One thing to keep in mind, though, if one of those machines go down and you don't have the RAID set very high, it's going to get ugly fast. The one upside of that approach, though, to traditional RAID systems is the recovery process looks a lot sweeter because RAM writes very fast, right? So, I lost 2 nodes. I have to repair all of this data. Yeah, it's going to take you like 3 seconds to write that out to recover it, and you're in good shape again.
This may be a bit of a naive question, but it seems like whenever you're talking about the network logging, someone could just take standard syslog and add UDP subscription to it, and boom, you have the automatic process that you're describing. So
syslog is mostly there. It's got a couple of... First of all, syslog by default originally was a UDP-based service, right? TCP was added later. So it actually was built around these principles. We just kind of forgot them over time. But the catch is, so it doesn't have the discovery, so you're right. You could tag it with multicast, and actually there are a couple... I think our syslog has a thing you can add onto it that'll do the multicast thing. But the other catch is it's still pushing out text, okay? The log information that's sent out is text. It's not structured data, which there's a huge win there from the structured data. You don't have to worry about the problems that come from, this payload confused my parser, and God knows what happened. It also, things process a lot more efficiently. And then the other thing is, if you look at the data that's I'm putting in that header, not all that data is in syslog. And that's very helpful for when you're trying to reconstruct the truth or figure out what went wrong when you do detect a loss, right? So that would be the other thing that you'd have to add to it. But you're right, it's a baby step. I mean, dude, I wish I could pretend that all this stuff was brilliant stuff that no one had ever thought of before. No, the stuff that works is the stuff that people have thought about before, and just it's doing it right.
And hey, and thank you for taking all those pre-thought up things and putting them all into order in a nice bunch of slides or into 6 envelopes and letting us open them up. So, hey, thank you very much, Chris Smith.